Okay, so welcome back, everyone. So today it's my pleasure to welcome Professor Youssef Marzouk, who'll be talking about sampling and generative modeling using dynamical representation of transport. Yeah, thank you, Youssef. Yeah.
Okay, thanks, Mehmet, for the invitation, and thanks to everyone for coming. I realized we had to reschedule this from 2 months ago because I was sick at the time, but so thanks for your flexibility in that regard. I still have a bit of a cough today, a whole different sickness, so bear with me if I have to pause and drink some hot water. In any case, so I want to talk today about a broad line of work that we've been doing that's really at the intersection of dynamics and sampling. In some sense, this is using dynamics for sampling, and in particular using dynamics to represent change of measure, to represent transportation of measure. And this is, as I hope to show you in the next few slides, kind of a broadly useful method for sampling, for generative modeling, for a whole host of kind of modern, sampling and machine learning tasks. So the people that have been most involved in this work are shown here. My main collaborators, current PhD student at MIT, Amy Moray, Panos Simpos is a second-year PhD student at MIT, and Robert Wren, who's also a finishing PhD student at MIT. And then 2 former colleagues from MIT who are now faculty elsewhere. Sven Wang was a postdoc with us for a couple of years. Now he's a professor in Humboldt University. And Jakob Zeck was also a postdoc before COVID, and since then he's been a faculty in Heidelberg in Germany. So they've all contributed to various pieces here. So, okay, the sampling problem. So, I mean, the sampling problem is probably, is really ubiquitous in applied math and statistics and machine learning with a whole bunch of applications. What do I mean by sampling? I'll give kind of 2, maybe broad flavors. This is by no means exhaustive. I'm not going to talk about rare event sampling and things like that, but I'll talk about kind of 2 canonical versions of the sampling problem. One is this problem where I want to sample from some probability distribution, but I have access only to evaluations of its density, its unnormalized density. So I can query the probability density function up to a normalizing constant, and yet I want to sample from the whole distribution. And where does this problem arise? Well, it is actually very much like the central problem of Bayesian statistics, and I'm not going to go into detail in this example. It's just a sort of an Earth remote sensing example where we're trying to learn the atmospheric, the concentrations of various trace gases in the atmosphere from satellite measurements. And you can write down the posterior distribution of these concentrations given the data, and you can write it down. This is the posterior distribution that I'm showing you here as a product of a likelihood function and a prior, and I don't know the normalizing constant. Computing the normalizing constant is a whole computational endeavor, really tantamount to sampling, but I want to generate samples from this posterior distribution over the parameters x, just given the ability to evaluate the 2 terms on the right of this proportionality sign. I should ask, can you guys see my cursor, the little hand-shaped cursor that I'm moving around?
Yeah, we see it. Yeah.
Okay, good. Okay. I'll just point with that since this is not an iPad, and unfortunately I don't get to draw. Now, this is a challenging problem because the target distribution is very often not in some canonical form. It's not necessarily Gaussian or even exponential family, and it's often very high dimensional. So I really need Monte Carlo methods of some sort to draw samples from it. And this problem also arises in computational chemistry and statistical physics, where essentially you might know the potential u corresponding to some distribution. The distribution is proportional to exponential minus u. The normalizing constant is unknown, but I want to generate samples, for instance, of these atomic configurations given that potential function. A different flavor of the sampling problem, one that's very popular these days, is generative modeling. And generative modeling is a sampling problem with a different input ingredient. Here we just assume what I have are samples from my target distribution. I don't know the density. No one hands me the density even up to normalizing constant. They just hand me a bunch of samples. And proverbially people say, well, there's pictures of cats and you want to generate more cats. But in some sense, each of these cats is a sample from some distribution over images. And given these as training data, now I want to generate more cats. And I use cats to be a bit flippant, but there's many nowadays, much more, more serious and more widespread and more impactful applications of generative modeling, as I'm sure you all know. But it is a sampling problem where, again, just given access to samples from a finite set of samples from some target distribution, I would like to sample IID independent and identically distributed samples from the distribution further. So there are many other sampling problems, but what I hope to kind of start with is the observation that transportation of measure provides a unifying approach to many of these different sampling problems. What do I mean by transportation of measure? Transportation of measure is essentially this idea that I want to represent some complicated distribution of interest. I'm going to call pi, and I'm going to elide notation for measures and densities. I'm just going to kind of mix it all up together because I'm assuming all my measures have a little bit of densities. So let pi be a distribution on RD, and I want to represent it as the transformation of some simple reference distribution rho on RD. And what do I mean by transformation? Essentially, I want to find a function from RD to itself that pushes forward rho to pi. And that's what this subscript sharp notation here means. T pushes forward rho to pi. And in more precise terms, what that means is if I want to measure any set under pi, I just have to look at the preimage of that set A under T and measure the preimage under rho. In maybe more intuitive terms, what this means is if I can draw samples from rho, represented by these blue dots, and I apply T to any one of these samples, the resulting samples will be distributed according to pi. So this is really nice. If I had such a T, I can realize the dream of all Monte Carlo methods, which is IID sampling, because if I can choose rho how I like, and I'm going to pick rho to be, for instance, like a Gaussian or a uniform, something very tractable, I can sample from it very easily. All I need to do then is evaluate this map T on those samples, and then I'll have samples from pi, and I'll be very happy. Okay, so if I had such a map T, this was essentially a solution to the sampling problem. And I can do other things as well. And just to kind of maybe set notation, I'm going to use the subscript sharp to mean push forward. So this is the distribution that I get when I transform an input distribution rho by T. And the pullback is essentially what I get when I apply T inverse to pi. So now I'm going to take samples from pi, apply T inverse to them, and I would get something that looks like rho. Okay? So the superscript sharp is pullback, the subscript sharp is push forward. Okay? And if the map is invertible and differentiable, then essentially I can compute the densities of the push forward and the pullback in closed form. It's really the change of variables formula. So there's a Jacobian determinant, and we'll see that explicitly in a few slides. Okay, so this is very nice. You might ask, okay, well, does such a map exist? And in general, yeah, a map achieving this push forward condition, transforming some rho to pi, exists under very mild assumptions on pi and rho. Essentially, if they don't have atoms, if they have limit densities, then I can always find a map. And in fact, my problem is really the opposite. There's infinitely many maps for simple pairs pi and rho satisfying these mild assumptions. And you may have heard of kind of certain canonical maps. The optimal transport map is one choice, was optimal under a particular cost. So I get to define a cost and then find an optimal map that is, if I can find a map that is optimal in terms of minimizing the integrated displacement cost or displacement squared or something like that. Noth-Rosenblatt maps, which are triangular maps, essentially the nonlinear analogs of Cholesky factors of SPD matrices, are another canonical choice. But in this talk, we're not going to limit our attention to these canonical transports. These may show up, but we're going to actually have cast a broader net because there's many, many maps that could do the job of sampling. And if I really care about sampling, then perhaps I don't necessarily care about achieving the optimal map or the triangular map, or some specific canonical map of that form. Okay. That's the way I should say. If you have questions along the way, please just ask. I'd be happy to pause and answer any questions that come along. So, okay. I've claimed the transport is useful for sampling, and if I could find a transport map, I could solve the sampling problem very easily. But so far, I have not solved the problem. I've only moved it. I've essentially said I've replaced the problem of sampling from some distribution on RD to one of finding maps from RD to RD, and in particular invertible maps that are sufficiently smooth. In general, what kind of maps do I want? I want invertible maps, and then for computational reasons, I want the Jacobian determinant of the map not only to be well defined, but to be easy to evaluate, because I'm going to need to evaluate this Jacobian determinant a lot when I do change the variables and evaluate densities and things like that. Now, there's really a multitude of choices that you can imagine that realize these general goals of finding maps from RD to itself that are invertible and that have Jacobian determinants that are easy to evaluate. And I'm going to categorize many existing approaches into two categories. I'm going to talk about static approaches, and then I'm going to talk about dynamic approaches. So what do I mean by static approaches? So static approaches essentially directly represent that map T. They essentially represent the displacement, like a feed in at point X, and then the static approach will tell me exactly where this point X that I fade in, exactly where it ends up. So it's essentially a direct representation of the mapping T. that's in this figure. Now, what are some common static approaches? Well, normalizing flows are popular in the machine learning literature, although their history goes back way before. Are essentially, compositions of simple maps and maybe interleaved with permutations, typically parameterized with neural networks. We've spent a lot of time thinking about triangular maps, monotone triangular maps, which are approximations of the Knuth-Rosenblatt rearrangement. And there are nice ways you can represent monotone triangular functions, essentially by applying some invertible rectification operators to common linear spaces, wavelets, polynomials, other linear spaces. Another option is to say, well, I want to find optimal transport maps. And one way of approximating that, since optimal transport maps, these Brownian maps are gradients of convex potentials, is to represent convex functions, for instance, using deep neural networks. So using input convex neural networks, or if I want conditional Brownian maps, I might use partially input convex neural networks. And various choices of this form have been proposed in the literature, and this is not in any sense a complete representation of, I would say, hundreds, if not thousands, of papers about how to represent displacements, how to represent the transport map directly. Now, there are another kind of category of approaches are dynamic approaches that employ evolution over some fictitious time. And so now we're sort of not representing the map directly. We're representing a maybe velocity or maybe a drift, something that when integrated gives rise to the desired map. So a very popular construction here is known as neural ODEs, and we'll talk about that in detail. Essentially, I'm representing the map as the flow map of some ODE. Flow matching methods are also very popular. Stochastic interpolance is a broad framework for understanding all these dynamic approaches. But in other contexts, many sort of ensemble common samplers, which are interacting, essentially realized as interacting particle systems, they also represent the transport in a dynamic way, essentially transforming some distribution on initial condition to some desired distribution later in time. And you can imagine discrete time dynamical systems as well. For instance, this paper uses kind of the Newton iterations to realize a transport map by iterating over some, index, some discrete time. Okay, so the dynamic approaches are kind of what I want to focus on today. And I want to talk about, they actually present some really interesting opportunities. They work very well in practice, but there's also a lot of challenges in their design and a lot of things to be understood about them. And that's what I want to spend the bulk of the talk on from here on. So what do I mean now more precisely about these dynamical representations of transport? A recurring structure is to say that the transport is represented as the flow map of an ODE system. So here's an system of ODEs. Capital X is essentially the state. It's actually the flow map. Little x is the initial condition. F I'm going to call the velocity field, or the right-hand side of the ODE. This is a non-autonomous ODE. And the idea here is, okay, for some x in some domain, time going from 0 to 1, I'm going to solve this, and I'm going to compute these trajectories big X. So the trajectories you can represent in closed form this way, or make this work in them formally this way. I'm going to have the superscript F to say this is the trajectory induced by a particular choice of right-hand side little f. And if I now just consider time to be fixed and consider this as a mapping of the initial condition to the state at time t with initial condition little x, this is the flow map. This is the time t flow map induced by the velocity field f and then the resulting ODE system. And without loss of generality, I could say, let me just consider time 1. This is the finite time that I care about. And this is now a transport map TF that is parameterized by velocity field little f. So this is the time 1 flow map of the system. Okay. So, okay, why is this representation useful? I'm just copying it above here. Well, one nice thing is that, under very mild conditions on f, essentially Lipschitz f, and then if you're on a bounded domain, there's certain boundary conditions, the flow map induced by this ODE system is guaranteed to be invertible. So very generic choices of function class are feasible. So in contrast with, say, normalizing flows, where I need to spend a lot of time thinking about how am I going to construct invertible functions, how am I going to make the Jacobi determinants evaluatable, so I can evaluate the densities. Here I can pick very generic choices of f. F does not need to be monotone or anything. F just has to be Lipschitz, essentially. And if I want to evaluate, say, the density of the state at some intermediate time t, given some density on the initial condition little x, I can do that quite tractably using what's called an instantaneous change of variables formula. Sorry, I think it's jumping ahead. So this is quite useful from the perspective of representing transport. And essentially, I can get invertible maps for free intuitively using the idea that paths of the ODE don't cross. So this is a nice representation in that sense. And in practice, these representations and their variants have achieved leading performance in many applications, many generative modeling applications, and also density estimation applications. So, okay, it's a nice representation, but there's a lot of sort of theoretical questions. From a theoretical perspective, one thing that's not well understood, at least until recently, is approximation rates, kind of statistical finite sample convergence guarantees for these kind of deterministic ODE representations of transport. How do these guarantees depend on smoothness of the underlying densities? And how do they compare to other kind of very classical methods for density estimation? This is essentially a much fancier method for density estimation and representing the density as the push forward of some reference distribution under a map. And the map is itself being represented by an ODE that is parameterized by some velocity. So this is a much more complicated machinery. How does this compare to other things, at least theoretically? And then maybe a more, I think even fundamental question, and one that has a lot of algorithmic implication, is what should we do with the freedom afforded by time axis? And to kind of frame this, let me point out that there's really two nested infinities in this problem. So one thing we already know is that given, say, some distribution at time 0, some distribution at time 1, there are infinitely many transport maps that will push forward this distribution to that. Okay? Even if these are just Gaussians, I could essentially take arbitrary square roots of the covariance matrix of the target Gaussian and get Cholesky factors, symmetric square root, various non-symmetric square roots, and each of them will give me a different transport that still realizes the desired push forward. Okay? So for any given reference target pair, there's infinitely many maps. That's one thing. But now there's an extra infinity, which is that for any transport map that I want to realize, there are infinitely many velocity fields that will give rise to that transport. And this cartoon illustrates that. I could essentially get the same displacement, say this point going to here, this point going to here, with these somewhat straighter lines, or I could take some excursion. I could have these I could wind around a little bit and still end up at the same point at time 1. So I could take essentially almost arbitrary excursions in between in finding my velocity field. And then the question is, well, does this help you? Or is this actually problematic? Does it lead to new challenges? So I want to kind of address these questions in part, and there's a lot of open questions, I think, still by the end of the talk, but I want to address some of these with a couple of vignettes. The first is about some statistical analysis of neural ODEs, some recent work with Robert and Sven and Jakob. So here's kind of the idea. We're trying to essentially uncover statistical finite sample convergence rates for learning ODEs, learning particular neural network representations of the velocity field in an ODE, and trying to understand the performance of these methods as density estimators. How good of a job can they do representing a desired distribution given finite samples? So to kind of set things up, I'll maybe gloss over some of the technicalities in the interest of time, but we have some minimal requirement on the velocities. Essentially, here's the domain in which the density is supported. Here's the time domain. I want them to be C1, and on the boundary of this domain, I want the velocity essentially to have a vanishing normal component. Under these conditions, then the flow map at any time t is a diffeomorphism, and I can write the pullback density. So essentially, under this map, I can now pull back any reference density rho, and I can write that pullback via change of variables formula in closed form. So essentially involves rho evaluated at the map, and then the Jacobian determinant of the map here. And now, given this, I can form a maximum likelihood training problem. So now essentially the problem is I have samples, xi, or I should say these xi's are now drawn from some target distribution of interest, call it pi. And I'm going to consider some class of velocity fields as a subset of this minimal class V. I want to consider the time 1 flow map that I'm going to call TF. And this, the change of variables formula, is essentially my approximation of the target distribution by pulling back the reference distribution rho under the map. So this is just this pullback density where I've substituted xf for any arbitrary time t with the time 1 flow map. I'm going to evaluate this log density at the training data. So this is the log likelihood. And now I want to find the velocity field f that maximizes this log likelihood in my class, in my allowable class of velocity fields. And this is now my estimate of the velocity field of the ODE. And since the xi are drawn IID from the target distribution, then the maximizer is itself random, and that's I'm giving this hat denotes that it's the estimate. This is my essentially maximum likelihood estimate of the velocity field of the ODE. So now to analyze this problem, we're going to make some assumptions. We're actually going to work on bounded domains, essentially the unit hypercube. We're going to consider the target density pi to be bounded above and below, the xi's or an IID from pi. We're also going to make some boundedness assumptions on the velocity that correspond to the boundedness assumptions on the target density above and below. And in this setting, what we can formulate first is a very general convergence theorem for what we call these ODE MLEs, so maximum likelihood estimates of the velocity field of an ODE. And this general convergence theorem, it's not actionable in and of itself, but it kind of shows the trade-offs that are intrinsic to this estimation problem. So first, essentially, I mean, maybe I kind of jump down here. Let me kind of show you what the main result is, and we'll talk about the ingredients. So essentially what we're saying here is we're kind of going to look at the Hellinger distance, that's what this little h denotes, between my approximation of the target distribution, given by the pullback of the reference using the estimated velocity field f hat, and the true target distribution. So here's the Hellinger distance between these two things. F hat is random, so I'm going to, and it depends on the n samples, x1 through xn, the n training samples. I'm going to look at the expected value of this Hellinger distance under essentially, different batches of sample size n. And this error, this expected Hellinger distance, is bounded by two terms on the right. One reflects the approximation error, so f star is any element of this class of velocity fields. And the second term is a statistical fluctuation that reflects the complexity of this class of velocity fields. How big is the class? And the idea here is this kind of, in finite dimensions, you think of this as kind of a bias variance trade-off, where the first term is bias and the second term is variance. So this is how well can I do? F star, you could think of it as, well, this holds true for any member of the class, but in practice, I'm going to want to set this to be a member of the class whose approximation error I can control, ideally some kind of best approximation in the class. And then this reflects the complexity of the class itself. Now, what notion of complexity matters? It turns out that it's essentially the C1 metric entropy of the class. So here's essentially the log of the covering number of the class, or here's the radius of the coverings. And the C1 norm is what matters for reasons that I'm going to describe in the next slide. And that's kind of one of the insights of this work. That's the C1 norm of the velocity fields that matters in terms of controlling the complexity of the velocity field classes that I might consider. Okay.
Hello, Youssef. A quick question. So
yeah.
Could you help me understand the basic? Do you assume that the expression of rho or pi, which one is the target density? Do you assume its expression is known or not?
Yeah. So rho is known. Rho is not the target. Rho is a reference that I pick. So this is sort of like a property. Rho is in our case going to be like the uniform measure. So rho is the thing, oops, that I want to map to my target. So I'm going to start with uniform and I want to warp it to get to my target. Pi is the target, but I don't know the density of pi. All that I have are IID samples from pi.
Okay, thanks. I see.
Yeah. So, okay. So this is now essentially how well I can do approximating pi in warping rho by the action of this map. And these are non-asymptotic bounds because this C does not depend on that. Okay. So, okay. So this is kind of, a general concentration result. There's a lot of detail that goes into it, but just to give you intuition, this actually comes from very general theory for M estimation developed by Sarah Vandegeer and others in the early 2000s. But it quantifies a trade-off between approximation error in the class F and the statistical complexity of F. And one of the key things is what is the appropriate notion of statistical complexity? We link this to the C1 metric entropy of the class of velocity fields. And why C1? Well, essentially, what we end up having to analyze under the hood is this kind of chain of stability results for ODE-induced maps. So consider two velocity fields, F and G. Their C1 norm bounds the C1 norm of the difference between two transports, the resulting transport, the flow map induced by F and the flow map induced by G. And this, in turn, controls L infinity error in the pullback densities. Okay? And if this is the thing I then want to control for Hellinger and other, kind of results on the density, that's why the C1 norm in the velocity field is what matters. But so the analysis, we kind of then have to go through and establish this kind of Lipschitz type bounds. So now, okay, this is a very general theorem, but now we want to apply it to something more practical. So the idea is, well, I have these two terms, let me bound them and balance them for some class of distributions pi. And now I get to assume properties of the distribution of interest, and then some approximation class f. And the approximation f class f can scale with the sample size. In other words, when I have small sample sizes, I might want to use a very simple class of velocity fields, because otherwise the statistical complexity is going to be very large, and it's going to overwhelm the approximation error in that class. But as the sample size gets larger, then I can afford to pick a larger class f and have a smaller approximation error, because I'm going to have more control over the fluctuations of the MLE because I have a larger sample size. So that's kind of the idea. Now I want to do this for the specific case of smooth densities. And the construction here is interesting. It's actually a construction that's going to show up later on in the talk. It's essentially to say, okay, suppose that I have a density that is Holder smooth, CK smooth, K Holder smooth. Then what we want to show is that there exists a velocity field that pushes forward, that pulls back the reference to the target so that it achieves the desired approximation, that is also CK smooth, intersected with our set that involves the right boundary conditions. And we're going to construct this explicitly. This will actually show this quite explicitly for a specific velocity field. And here we're going to use the Knuth-Rosenblatt map as the specific map whose velocity field we can then realize that then achieves this coupling. Now, the Rosenblatt map is a triangular map, and it has a lot of nice features. Analytically, the nice thing is you can essentially write it down in terms of CDFs, conditional CDFs of the target distribution. So it's a very nice tool in that sense. I'm going to consider the Rosenblatt map, T, but I'm actually going to consider a straight line interpolation of T. So this is essentially saying when T equals 0, this map T sub 0x is the identity. I haven't moved at all. And when T equals 1, then this map is just the Rosenblatt map capital T. And in between, I'm going to interpolate particle positions between their endpoint and their starting point. So this is a straight line interpolation of the map T. What I can construct explicitly is a velocity field, which is a function of space and time, that realizes this straight line interpolation. And instead, here's the construction explicitly, but maybe a picture will show you, more explicitly. I'll show you a picture in a second. But the point is that this result is that this velocity field, the straight line, the velocity field that realizes the straight line interpolation of the Rosenblatt map is itself CK smooth. So this velocity field inherits the smoothness of the target density, and it satisfies the desired coupling condition. What does this velocity field look like? Maybe here's a picture that makes it more clear. If here's time 0 and here's time 1, I have a transport that takes x to t of x, and it takes x prime to t of x prime. This happens to be the Rosenblatt map. In 1D, you can't tell because these maps look the same. But the straight line that interpolates them is given by the black here. And the velocity field that realizes the straight line, in general, is a function of space and time. But what it does is it maintains zero acceleration in a Lagrangian sense of any particle. So if I start off at a time t here, and I want to know what is the velocity field that this particle should undergo, or if I want to know the velocity field at any point in between, well, I sort of say, okay, what is the initial condition that brought me to the state, to this value of the state at this time? Walk back here. Then look at t of x minus x, that's the total displacement I need to undergo, divided by time, which is the unit. And that's the velocity field that's the velocity that I must feel instantaneously at any point along the way between t equals 0 and t equals 1. And that's exactly what's happening here. This f takes me back to the initial condition. This is t evaluated the initial condition, that's the endpoint. This is the big initial condition itself. And the velocity field is just equal to the difference because we're unit time. But at different places, the velocity field will be different. So this is a zero acceleration in a Lagrangian frame, corresponds to the straight line interpolation of the transport t. Okay. So this is something we can now show. There exists a velocity field that does this coupling, and this is then what we're going to use as our to compute the approximation error in our general concentration inequality. And then we need to set the class of velocity fields that we search over when we compute the maximum likelihood estimate. And we're going to consider, we want to apply this to neural ODEs, so I want to consider neural network classes. And here we can borrow neural network approximation results. and essentially say, well, how well can I approximate this particular velocity field, which has this kind of regularity, in a neural network of a given size, and the size is controlled by the length, the width, the sparsity, bounds on the weights, and then this bound on the W to infinity norm. So we can define these neural network classes, and now essentially come up with appropriate scalings for the class with the sample size n. Remember, n is the number of training samples I have. Put all these things together and construct a kind of final bound for the statistical error of the neural ODE estimator over this class. So the neural ODE estimator of the velocity field over this class of neural networks with this particular scaling with the sample size satisfies this bound. So this is a statistical finite sample guarantee for neural ODEs. And essentially, it involves the smoothness of the class, densities K, and the dimension D of the densities. So this is the kind of putting it all together result. Now, this is kind of in the vein of a lot of results in non-parametric statistics. So we will think of this as kind of using a non-parametric analysis of neural ODEs. To our knowledge, this is the first statistical convergence result for these kinds of ODE representations of transport. So that's we're excited about that. But if you're seen this kind of literature before, you might say, okay, well, how does this compare to known optimal estimators? So this result that we had, this is the result from the previous slide, had k minus 1 in the numerator and k minus 1 and t plus 1 in the denominator of the exponent. I can compare this to the known optimal minimax rates for density estimation. This is the best that one could achieve. And there's a little bit of suboptimality here. We had k minus 1 rather than k, and we have d plus 1 rather than d. Now, is this kind of a deficiency analysis? Actually, it turns out that this has some more fundamental causes. And these fundamental causes are interesting and get back to this question of time freedom. So why k minus 1 rather than k? That's actually more of an annoyance and it's somewhat technical surmountable. But why d plus 1 rather than d? The fundamental reason is that we are now searching, we have an extra dimension of time. We're searching for velocity fields that are functions of space and time, and they're essentially unconstrained other than this generic neural network representation and the scale of that neural network representation. So that is something this extra degree of freedom comes to bite us when it comes to these convergence rates. So my heuristic argument here is that somehow in searching for generic time-dependent velocity fields, we've allowed ourselves too much freedom. And this has been noticed, sort of soon after neural ODEs were introduced, people started using them. Maybe a year or two later, people started saying, well, maybe I should regularize the training objective. And there's a lot of papers that try to do this. Or more recently, what people do is they kind of depart from this maximum likelihood training regime. And they start imposing target marginal distributions at intermediate times. I'll have more to say about that later. But this is essentially the idea that somehow we might have too much freedom and we need to tame it in some way. So I'm going to talk about sort of two ways of taming it. This first one I just want to talk about very briefly because it's work in progress. This is an ongoing collaboration with Jose Blanchett at Stanford and his student Hashwan Chen, along with Robert, Sven, and Jakob, and myself. And essentially what we're saying is, okay, if you're searching for generic functions of space and time is too much, can we come up with a more restricted ansatz that actually recovers optimal statistical convergence rates? And okay, it's no surprise based on what I've told you so far, somehow time and space should not be treated equally. And our idea now is to come up with a different velocity field ansatz that represents the transport as a composition of near identity functions, but a finite number of these that depends only on t and not on the sample size. And these are near identity in that these perturbations to the identity are Lipschitz. So what are the key ideas with ansatz? Again, we're going to begin with this Noth-Rosenblatt map. Can show that we can represent the Noth-Rosenblatt map as a composition of m near identity maps. And then we're essentially going to partition time into the m intervals. And on each interval, we're going to seek, for the purposes of constructing the approximation result, the straight line velocity field that realizes this transport. Now this, essentially borrowed from the earlier slide to show you, is an equivalent expression for a velocity field that realizes the straight line transport. And you look at this inverse here, how do I accomplish it? For th being small, one way to think about this is actually via fixed point iteration. So if I unroll this inverse and start to write this out with a fixed point iteration, then essentially I can approximate this velocity field as sort of what I get with an infinite number of iterations here. Here I'm going to approximate with some finite number j of iterations that come from this. And this is now an approximation of the straight line velocity field that has this inverse here, it starts to look a bit like a ResNet. And it actually starts to look a lot like a ResNet because these fixed point iterations look like a ResNet. And this now kind of gives rise to a velocity field onset. So here's kind of the idea. I have partitioning time onto these intervals. On each time interval, I'm going to represent the velocity field as this function phi I, which is essentially comes from j fixed point iterations. And visually, maybe this is a kind of a cartoon of what's happening here, time 0 to time 1. I'm partitioning time into a finite number of intervals, and then I have this representation of the phi, which is the local velocity in time on each interval. And I can construct an appropriate neural network class. And now this is work in progress. So I'll say this is a conjecture, but I think we're very close, modulo some technical details. Our conjecture is that this more refined, more restricted ansatz for velocity fields actually does achieve the optimal min-max rate for density estimation. But the point here is we've somehow taken away freedom and used the specific structure of the straight line velocity field and approximating it as a ResNet. So it's a much more refined ansatz than in the generic neural ODE world, where you just have some generic ODE right-hand side represented as some fully connected whatever neural network. Okay, so stay tuned for that. I think the paper is hopefully in a month or two we'll have the paper out on that. So the takeaway here is that this is a way of taming the time complexity of dynamical transport. And maybe the idea, maybe the take-home idea is that being incremental seems to be helpful, but being arbitrarily complex in time is not. So given that, I want to kind of talk about a second vignette, which takes to heart the idea of controlling what happens in time. So now I want to get into a different vein of dynamical approaches that by, we're constructing them now so they don't involve any neural network training or optimization. So this is not something that involves training. What we really want to do is construct a dynamical system that I could realize, that I could write down and then realize and, essentially write down in closed form, that approximately samples the target pi1 in unit time. And so a preview of what we're going to do is we're going to create a mean-filled ODE, and we're going to realize it with some kind of interacting particle system. So this is, shift gears, and this is not a neural ODE, it's an entirely different approach. But it is still a dynamical representation of transport that at time 1 wants to approximate the desired reference measure, or target measure. So, okay. So now let's consider, let me on the pi 0 represent the reference measure, and I want to consider the following sampling settings. So this is now a different setting than I had before. I don't have samples from pi 1. Now I'm in the kind of classical, unnormalized density setting where I can evaluate pi 1 over pi 0 up to a normalizing constant. I also assume that I can generate samples from pi 0 from my reference distribution, which is fair because that's something I might pick. Or pi 0 might be the prior in a Bayesian inference problem. Pi 1 might be the posterior, in which case pi 1 over pi 0 is the likelihood up to a normalizing constant. Further, I'm going to assume that I don't have access to gradients at pi 1 or pi 0. So I'm going to construct a gradient-free sampler. Why is this setting of interest? Well, encompasses the standard setting for Bayesian computation. This is also precisely the kind of problem setting you encounter when you think about data assimilation. So data assimilation is a problem where essentially we only know the prior through samples, and the likelihood is probably tractable, but I want to then somehow give in samples from the prior, which I call the forecast distribution in data assimilation. The ability to evaluate the likelihood, I want to generate posterior samples or some good approximation of posterior samples. Typical algorithms in the setting could be sequential Monte Carlo or ensemble Kalman type methods. Okay? And there's a zoo of such things, and these are widely used algorithms. But they all have, sequential Monte Carlo has drawbacks in terms of scalability, and ensemble Kalman methods, as I'm sure you all know, are only approximate. They're not consistent with the true Bayesian posterior. Okay, so how are we going to do this? We're going to kind of go to the other extreme of now prescribing the marginals of a path of measures at every single instant between time 0 and time 1. So we're going to prescribe this path, and now I'm going to try to find a velocity field for this ODE that realizes that path. So first question is, well, what path should I pick? I need this path to be tractable in the setting that I described, where I don't know I can only evaluate pi 1 over pi 0 to a normalizing constant. So one path that first comes to mind, this is kind of our first choice, but it's a very natural choice, is what's called the geometric mixture. So this is essentially, you know, a path pi t where I'm taking pi 0 to some fractional power, pi 1 to some fractional power, but at time 0, I correspond to pi 0, and at time 1, I correspond to pi 1. And this is an example of that geometric path. And so now we want to find an ODE. An ODE, it's a mean field ODE, so the velocity field might depend on the instantaneous measure of the state, the law of the state at time t, that achieves this path. So I want the rho t's generated by this ODE to approximate pi t. So what is this path? I mean, just kind of step back and think about this path. There's actually many, many ways you can think about this path. One thing I should point out is that the time derivative of the density along this path involves essentially the log ratio of the target over the reference. Right? And this log ratio is tractable. Essentially, this is the log ratio centered, the log ratio minus S expectation. Now, one way to think about this path is that it actually corresponds to a Fisher-R gradient flow. So gradient flow in the Fisher-R metric of this particular functional. This particular functional is essentially the log likelihood. And I'm running it from time 0 to time 1. If I ran this to time infinity, I would end up at the maximum likelihood estimate. But this is over a finite time, over this 0 to 1 interval. This path corresponds to that interval of this gradient flow. Another way to think about this is a unit time rescaling of the Fisher-R gradient flow of the KL divergence, the forward KL to the target. And that's described very nicely in this recent paper, where essentially this is the rescaling of time. And then yet another way to think about this path is that it's a path of KL barycenters. Suppose I want to find a distribution mu that is somehow equidistant or weightedly equidistant between the reference distribution pi naught and the target distribution pi 1, and the weight is given by the time. So this is barycenter of pi 0 and pi 1, and the barycenter moves with time. That again corresponds to this path. So many lies of this so-called geometric mixture.
Okay, Youssef, so now you have to know the expression of pi 1 or not.
Yes, absolutely. Yeah. I'm told now I'm in this different setting. I have to know, well, I have to know pi 1 up to a normalizing constant.
Oh, okay.
Yeah.
Good.
And
Yeah.
in fact, I only really need to know pi 1 over pi 0 up to a normalizing constant.
Yes, okay, great.
Yeah. So I say that's important because there are problems where I might actually not know the prior, but I only know the likelihood. Like I only have samples from the prior, but I only know the log likelihood.
Okay, thanks.
So how to solve this? So you can kind of appeal to fluid mechanics intuition. Long ago, I used to do fluid mechanics. Well, the velocity field that realizes this path of densities has to satisfy continuity equation. These first two terms here are just the continuity equation. And I know the time derivative of the density, then well, I can just compute that through simple algebra, and here it is. And okay, now the thing is there's many velocity fields that can satisfy this continuity equation. There's in some sense kind of a divergence-free part that's irrelevant. So of all the velocity fields that I want, which one do I aim for? Well, let's consider kind of the minimum energy onset. Let's look for the velocity field that is a gradient of a scalar potential. And if I plug that in, then what I end up with is this Poisson equation. So Poisson equation is essentially with this pi t weighted Laplacian on the left, and the right-hand side that comes from the choice of path. So the choice of path has dictated the right-hand side, and the left-hand side is entirely due to continuity and the desire that I'm looking for the velocity field as a gradient field. Okay, so now essentially what we need to do is just solve this Poisson equation at each instant in time, find the velocity field, move particles, solve the Poisson equation again, and so on and so forth. And how are we going to do this? Well, we're going to kernelize the whole thing. So I'm going to solve this Poisson equation in the weak form. I'm going to seek its solution essentially in some RKHS with kernel K. So here's my ansatz for the solution, for the potential. And I plug it in, I do a bunch of algebra, and essentially what you can end up with is this closed form expression for the potential in terms of essentially kernelizations of the solution operator of the Poisson equation. So these are integral operators that involve the kernel, and you can sort of write this all down. Okay, so if I do this now, and I come back to the ODE that I wanted, then this is the mean field ODE system that I want. So essentially here is the time derivative of the state at time t, and it depends on this whole right-hand side that involves an expectation over the law of the current state. And if I do this, I can evolve so that xt, the law of xt approximates pi t, and the approximation is due to, well, the fact that I've approximated the the solution in some RKHs. Okay. Now I'm going to discretize this with J particles, so that introduces a further level of approximation. But now what I have is an interacting particle system that I can write down in closed form. I can evaluate these things. All I need to do is begin with J samples from pi naught. I need unnormalized evaluations of this log density ratio. It's gradient free. I don't need gradients of anything, and it's closed form. And one way to think about what this is, what we've done effectively is we've taken the Fisher-Rao gradient flow, which you could, normally think of as like a reweighing of things, essentially bleeding in the weight that comes from the likelihood gradually over time. And we've Wassersteinized it. In other words, we've taken what you would normally approximate by reweighing and instead say approximate that by moving the particles rather than reweighing them. So we've essentially find the velocity field that realizes this Fisher-Rao path. So it realizes a path that corresponds to reweighing, but we're realizing it by pushing particles rather than introducing any weights. So that's why I like to think of this as kind of Wassersteinizing the Fisher-Rao gradient flow. Now, okay, here's this mean field system. I should say, there's different perspectives that can yield the same mean field system. In our paper, we also describe a way to arrive at the same thing by applying what's called sample-driven optimal transport. This is an idea from Kwong and Tabak. There's a concurrent paper from Nick Nuskin and then Feng Wang that arrives at the same kind of ODE system via kernel mean embeddings. And I'm sure there are many other ways at arriving at the same system. So how does this work in practice? Here's a little movie. So here's kind of I'm starting off at a Gaussian at time 0. I'm running these particles, and here's how they evolve to the ring. And I'm showing you both kind of the desired evolution, sort of the Fisher, in the contours is the desired pi t path, and then the red are the particles that realize it. And this is in the eyeball sense, it seems to work well. You can compare this, here's a bunch of other kind of non-Gaussian examples. You can do these things that actually push the particles to multiple modes. And this is just a slice of the evolution over time. And you can also compare this to other derivative-free samplers. You can compare this to like ensemble common inversion, which is not, an ensemble common sampling, which are not meant to be exact. Also compare this to things like consensus-based sampling and so on and so forth. This is just increasing the number of time steps. So how finally do you discretize time? And this is for 400 particles. Okay, so what we've developed so far, it's a nice method. It works on, I'd say, low to moderate dimensional problems. This problem, not using this method to solve 1,000-dimensional problems. I want to be clear about that, at least not yet. There are a lot of questions we still need to address. You can think of this as kind of a prototypical method that says, if I decide I want to achieve a certain path from pi 0 to pi 1, and this path is tractable in the sense of it requires maybe only unnormalized density evaluations, then I can solve a series of Poisson equations. I can kernelize the solution of the Poisson equations to realize this path via a system of interacting particles. But there's many questions you should then ask. Okay, if I like this Fisher-Rao path or this geometric mixture, should I proceed uniformly in time, or should I maybe take a different clock speed? And that's one question. Why this geometric mixture? It's very tractable, but there are other paths that are tractable. There's paths that have been used in yield importance sampling. There's different paths that have been suggested for yield longevity dynamics. Many paths that, in various corners of literature. Not all of them are tractable in this framework, but some are. And so which one is best? Maybe the bigger question is, well, what should I even mean by best? And here I would say we need to really relate the notion of the choice of path to some of the things that I talked about in the first vignette, which are how well can I approximate the velocity field? In this case, if I'm using kernels and finite particles, how well, there's velocity field approximation error there. There's also time integration error. And of course, there's sample efficiency. So these are, I think, broad questions in my mind, largely unanswered. Similar questions apply to recent sample-driven methods as well, flow matching and stochastic interpolants, which are different from what I would describe because they assume you have samples from pi 1 rather than oracle access to the unnormalized density. I should also mention a couple other, broader questions related to this kernel Fisher-Rao flow, which is, how do we make this more efficient at large scale? Things we're currently working on. So very naturally, you could say, well, I could use like random Fourier features, ways of approximating these very large kernel matrices. Also, what low-dimensional structure should this weighted Poisson equation inherit from the associated distributions? I think this is a very key question because the weighted Poisson equation is really central no matter what path I choose. And so something we're thinking about lately is localization, how Markov properties of the target might be reflected in variable dependence of that potential. And yeah, I underscore this is important because I think similar Poisson equations appear in a lot of other sampling schemes. And in some sense, whenever you want to kind of Wassersteinize a path or find a velocity field corresponding to some desired path, you will end up solving equations like this. But what I want to do in the very last 5 minutes is come back to a bit of this question of optimal paths. And I'm going to address, this is, I'd say, a first take, a very, very limited version of this question, but this is one for which we've been able to obtain some clean results. But I'll begin with the kind of the general open question. This is the last vignette. You know, if we're going to think about dynamic transport, this question even arose in the neural ODEs section. What is a good path from the reference to the target? In kernel Fisher-Rao flow, we pick this geometric path. In the vanilla neural ODEs, I'll let the path be anything I want. In the more refined ansatz, we're kind of making the path be this kind of like, you know, piecewise smooth velocity field. But in general, what should you pick? You know, I don't think there's a general answer. It depends very much on the method. But just to kind of take inventory of what we've seen. So neural ODEs, vanilla, have essentially no specification of the path. They're just concerned with maximum likelihood training based on the endpoint. So they care about where you are at time 1. What you do before time 1 is your own business, and that might be too much freedom. Regularized neural ODEs, one thing you see a lot in the literature, people try to find the straight line path for some transport, and maybe that's the optimal transport. Our new ansatz, you know, work in progress, is we don't specify the path, but we somehow limit the freedom to achieve optimal rates. We say we have this piecewise smooth ansatz. But in the setting of KFR flow, we prescribe the path, we prescribe the geometric mixture path. In stochastic interpolants from Albergo and Weinenainen, they essentially prescribe the path implicitly by operations on samples because they're in the sample-driven setting. Rectified flow from Chang Liu and others iteratively seeks a straight line path. And you know, many other things have been proposed. So I want to kind of, in my last few slides, address this question of, well, are straight line paths really what you want? Because this is something you've kind of seen. There's a widespread folklore in the community that straight line paths are the best thing to do. And we certainly use straight line paths, straight line interpolants of a given transform map T in our excuse me, in our analysis as a theoretical construct of something you can understand very well. But you know, what's the rationale? Well, the rationale is if I have a straight line path, I have 0 time integration error. I can essentially take one explicit Euler step and exactly realize the transport. But I have to say this has always bothered me because if you're going to construct a straight line path, your velocity is entirely determined by your velocity at time 0. And so what's the point of being dynamic in the first place? You're essentially, you know, if I just jump back to my figure here with straight line paths, the velocity is entirely determined. The velocity does not change in the Lagrangian sense. So there is no freedom in f of xt beyond the velocities that you specify at time 0, which in turn come entirely from the specification of a given transport. So why you're not really using, it's kind of the other extreme, you're not really using the time freedom in any way. So I contend that the optimal choice lies somewhere in the middle. So in particular, we need to balance velocity field approximation error and time integration error, rather than just trying to say the time integration error is going to be 0 and the velocity field approximation error can be whatever it is. And what I hope to show in these last 2 slides are that straight lines are not necessarily the best thing to do. So how to find what is. So I'm going to begin with a very simple example, but I think it's kind of illuminating. Consider the transport from one Gaussian to another, both of them centered at 0. I can write down the transport. It's linear, it's very easy. And here's the velocity field that realizes the straight line path. This is, as I said, is a function of space and time. Now, if I look at the Lipschitz constant of f as time approaches 1, and consider now the target at time 1 to be very concentrated relative to the reference. In this case, the gradient, and thus the Lipschitz constant of the velocity, spatial Lipschitz constant of f at time 1 will blow up as time goes to 1. It's going to inherit this essentially sigma 0 over sigma 1 scaling. Okay? And you can think about this as because all these straight lines that begin, say, at time 0, kind of fanned out, they all need to converge on this very concentrated target density at time 1. And if I look at the gradient in the spatial direction at time 1, just kind of following my finger horizontally, that gradient is very large because the velocity needs to change very rapidly over a very short distance, corresponding to the support of the distribution at time 1. So could I fix this by rescaling time? Turns out the answer is yes. So if I reparameterize time with some clock, so this clock tau is a reparameterization of the unit time interval. It has to satisfy 0 at 0, has to be 1 at 1, and has to be increasing. So it's essentially a monotone function from 0 to 1 pinned at the endpoints. I can write the velocity field with this rescaled time, and it would end up something like this. And now I have an opportunity to pick a non-identity tau, which effectively is going to give me a curved path to improve the spatial regularity of the velocity. So how did you know, and why do I care about the spatial regularity of velocity? Well, this controls the approximation error, appears in neural network approximation results, and also appears globally, it appears exponentially in sort of global time integration error bounds. Okay, so how could I do this? Suppose I want to now minimize, essentially I want to find the worst case gradient over spatial gradient of the velocity field, where f is some tau straight line interpolation of a given transport map. So when it says I'm solving a very limited problem, I'm saying you handed me a transport. I don't care what kind of transport it is, but you handed it to me. And now I want to find the best way of realizing that transport with a given velocity. So, and I want to find the best way of realizing that by rescaling the time of what was originally a straight line interpolant. So essentially, I'm going to solve this problem here. And well, what I can do, I can actually formulate this problem quite nicely. Well, I can relax this L infinity to L2p for large p. I define these quantities that essentially extract the necessary information from the transport. These are essentially the largest eigenvalue of the Jacobian of the transport map, -1, and the smallest eigenvalue. And these correspond to essentially where things are going to expand and where things are going to contract. And I can recast the problem essentially by writing this Lagrangian and minimizing the action of this Lagrangian. This Lagrangian involves these functions f and g and the tau. So here's this Lagrangian's function of time, the clock, and then the clock speed, tau prime. And I can solve this via Euler-Lagrange equations, and I'll stare you the details of the solutions given by simple ODE. And essentially what you find is that an optimal schedule slows time at the start of the trajectory or at the end of the trajectory, depending on how pi0 is concentrated or how pi1 is concentrated. So here's a bunch of examples, 9 different examples of optimal schedules, just for initial and target Gaussian. So Gaussian, the initial reference distribution is in blue, the target is in red, and you can see these Gaussians concentrate in different directions between time 0 and time 1, different things. And the schedules are essentially maybe S-shaped, or a piece of an S, or another piece of an S. Yeah, depending on whether things concentrate. Sorry, was there a question? Sure. Okay, I'm almost done doing it, and I realize I'm running a little late on time. But
No, it's okay. There's no time limit actually. Yeah.
Oh, okay. Good. Then I won't rush. But yeah, so basically these correspond to pieces of an S, or not, depending on where the concentration happens. Now, okay, so why is this helpful? I want to go back to this very simple Gaussian example. Here you can write everything down analytically. The optimal schedule actually looks like this. And now the spatial gradient of velocity actually becomes constant over time and space. And you can see the constant value, which is of course the worst case then, it now involves the log of the ratio of standard deviations. So this is exponentially smaller than what we had with the straight line path. The straight line path had this, sigma 0 over sigma 1. Now we essentially have the log of that. And so in norm, this is exponentially smaller. So we've won a lot. And essentially what this does, in the case of sigma 1 being very concentrated with respect to sigma 0, is that you have these paths that sort of begin like this. And then instead of all zooming into a point as sigma 1 goes to 0, they fan out. They essentially become kind of almost vertical at the end. So you slow down time at the end around the point of concentration, and you end up with a velocity field that is, in this sense, going to be much, much easier to learn, much, much easier to approximate. So the takeaway here, I mean, it's just in this very simple terms, it's kind of interesting. If I want to realize an optimal transport map, the velocity field that realizes it best does not correspond to the straight line interpolation. And in fact, I'd say, it does not correspond to, in this 1D case, I mean, the linear transport I wrote down is the optimal transport map, because in 1D, the simple monotone rearrangement is the optimal transport map. Basically, the Wasserstein geodesic, the velocity field that realizes that moves along that at constant speed, is not the nicest velocity field to approximate. I should slow down at the beginning or the end. So that's kind of, in my mind, a surprising result. But this is, of course, just scratching the surface of how to design optimal schedules and optimal paths. So, you might ask, is there some universal parameterization of the schedule? Should you, in general, is this idea of slowing down at the beginning or the end or both, is that sort of universal? Maybe I could, be more elaborate and take different speeds in different directions. Maybe that Lagrangian that I showed you can be actually incorporated into regularization terms for learning the velocity field. In that sense, we wouldn't be first prescribing the transport and then just trying to find the velocity to realize it. We would be learning the velocity and hence the transport implicitly. But constraining our attention to velocity fields that are tau straight, meaning straight according to the rescheduled time for any candidate t. And of course, then you need to analyze not just the velocity approximation error, but also the time integration error and put that all together. So it's a lot of work in progress. Similarly, we're doing a lot of work to kind of scale up these particle systems for kernelized gradient flows. But the underlying question of what to do with the dynamics, what dynamics to choose, what path to choose, what schedule along that path, I think are the cross-cutting questions. And that's something that I think is yet to be fully exploited, but hopefully we'll get there. So with that, I'll thank you for your attention. A lot of what I talked about is in these two papers that just appeared this past year, and I'd be happy to take any questions.
All right, thank you very much. Thank you. Any questions or comments?
Hi, Youssef. Thanks for the talk. And also,
long
time no see. So, I forgot my question. Okay, so the question is, what's the argument against, or what's wrong with the Langevin method or score matching? Is there a general remark? Because in the second part of your talk, pi1 expression, right? And I suppose you can do Langevin.
Yeah, you absolutely could. So I mean, my contention is that these interacting particle systems are okay. This is my empirical contention because I don't have sort of proofs about speed. I mean, methods are very new. Is that these kinds of interacting particle systems compared to Langevin dynamics, because they essentially get global information about the whole target distribution because they have particles everywhere, are better at capturing multiple modes, as we've seen empirically. And in general, they have a lot of parallelization. And they're also, in some sense, guaranteed to get there at time one. Of course, like with infinite particles and perfect approximation and so forth. But we've essentially moved the problem from mixing to one of approximating a velocity field. So yeah, so we've transferred the difficulty, and then my hope is that the difficulty is more tractable. Well, essentially, we've moved the sampling problem to one of solving PDEs. This is essentially what we transferred the problem to. And solving the PDEs with these kernel methods in some global sense that approximates the intermediate distribution. The other thing I would say is that we benefit compared to like vanilla Langevin dynamics from the ability to anneal. So by doing these things incrementally, and people now do anneal Langevin dynamics too, which is kind of similar in flavor. By saying you're not just trying to get to time one, you're not using the score of pi right at the beginning, you're essentially going to create a whole schedule for getting there over time. The hope is that you can do better and that you can come up with lower variance estimates. Although I'd say for these methods, the theory is still not there.
Okay, I see. And also another question, also the basic, and why do you want to minimize the gradient of f? Like you say it's less error prone, but where is the error? Like if you don't do that, if you don't do the time reparameterization, you just have a linear map, there is no error. So what error?
Wow. No, the point is okay, you have no time integration error, but you never get actual f. You get some approximation of f. And I would much rather approximate a function with smaller Lipschitz constant, smaller spatial constant than some very high Lipschitz constant. So the point, this actually shows up in like the neural network approximation results that I showed you earlier. These depend very much on the regularity of f. And so the spatial regularity of f.
But didn't you have an explicit expression of f already? No, or
no, because if I knew the transport, I have an explicit representation of f. But that's just kind of a theoretical device. In practice, I just have a bunch of samples, or I have the target density, and so And so I want to construct a class of I want to construct an approximation class for this velocity field that's going to do a good job. And by rescaling time, I know that essentially a smaller approximation class will be able to do a better job.
Okay.
And so I'm essentially making the learning problem easier by rescaling time. Let's do that.
Okay. Great. Thanks.
Right, thank you. Any other questions?
Yeah, is the optimal transport supposed to predict the trajectory?
So Hello? The optimal transport essentially only tells you where the endpoint should be. And let's say the optimal transport is one choice. There's many other choices of transport, but the optimal transport will say, okay, if you handed me the optimal
details
transport,
of the trajectory?
no, so if you handed me the optimal transport map, all you're telling me is essentially where a point here at time 0 should go at time 1. But you're not telling me where it should be in between. Now, if you say, okay, I want to linearly interpolate the optimal transport map, that is an additional request. That's an additional sort of ingredient. And that'll be like the McCann interpolant of the optimal transport map. And that would correspond to straight line interpolation of the optimal transport map. But I could do other things. I don't need to do straight.
Okay, I may be confused, but one of the definitions of entropy is how many trajectories you can have between 2 points. So are you using this implicitly in your C1 entropy?
Okay, that's good. That's a good, I mean, that's not the definition that we were thinking of. Because this is simply a statement about how complex the class of velocity fields that I'm going to consider is.
Okay, it's a measure of the complexity,
Of
entropy of the chaos and implicit chaos. So I have a question about the straight line.
Yeah.
Because it's considered convex combination, right?
Yeah.
Okay, now convexity is very basic help or sometimes essential condition for reaching the optimum. So it could be that, how about non-convex consideration?
Yeah. Right, so this is indeed a convex combination of the map T and the identity, but this is not related to the convexity of any optimization problem that we solve.
Okay, thanks. I thought so, but
distinct. Yeah.
I'm learning. It's only a learning exercise here.
Yeah.
Okay.
Because we're optimizing over velocity fields, and that problem is in general very non-convex.
Okay, now I'll show my ignorance, but it's based on fluid dynamics. Shear instability is not there, and the two straight lines that you have shown, the vectors are so different because the slope, I believe, difference, and then could be a shear instability, but we are not doing physics here exactly.
Yeah, it's not a real fluid.
So there is no instability, right?
No.
Okay. Appreciate your.
I'm only doing continuity. There's no momentum equation here. There's no momentum. There's certainly no, diffusive stress. So yeah, there's no like real fluids here. I'm just doing continuity.
Appreciate your mastery of all these concepts and connecting to neural networks and so on and so forth. Always learning. Thank you very much.
No, thanks for the questions.
Sure.
Yeah, thank you.
Okay.
Other questions or comments?
Youssef, I have one more question. So on page 16, you have a stability result, but it does not involve the time. So is this because it's time one interval? And if it's not time one interval, there should be another exponential factor with respect to time, right?
Oh yeah. Like we use Gronwall in here, but we just fix time one, so it all gets hidden in some constant somewhere.
I see.
Yeah.
Yeah. Okay, great.
Yeah, but the point is it's finite time, so
Yeah.
it's finite time as much as would be time one.
Yeah, of course. I'm just clarifying some. Yeah.
Yeah.
Thank you.
Yeah, this is, I mean, I skipped over so much technical detail over here, but in this paper, this JMLR paper I showed at the end, we walk through it in much, where did it go? Yeah, in this paper, we describe all of it.
Okay.
All right, thanks. Other questions or comments?
Well, anecdote. I attended a defense yesterday about relativity and geometry and Ricci curvature and all that stuff. And the fellow was, in a very clever way, was using space-time, and you mentioned space-time as well, but his trick was to do a time slice the space-time and analyze it to his advantage. I wonder if this could be useful here.
Like a slice at a particular time.
Yeah, you do a time slice.
Yeah.
Of the space-time.
Yeah. Yeah, I have to think about that. I mean, I would say like that does certainly, in some ways, this does show up. I mean, for instance, when we start to look at this is looking only at the derivatives in space of a velocity field that in general depends on space and time. But then we're looking at the first case over space and time of the spatial derivative. Yeah, I think it does. It probably shows up in a lot of different subtle ways here, but it's an interesting comment.
I can get you the reference if necessary, if you're really curious. It happened at UT yesterday in the math department.
Okay.
It was a beautiful, beautiful talk by, I can't remember the name, Mohammed somebody, but anyway, all the best to you. Sorry if I'm talking too much.
No worries, no, I appreciate it.
Yeah, thank you, Itamar, for the comments.
Sure, all the best. Yeah.
Thank you. Thanks. Yes, so just
Everybody.
maybe like a question about the Markovian. What you were mentioning something about the Markovian property. I mean, is this something that you are showing for all the dynamics independently of the kernel, or?
Oh yeah.
I missed the comment. Yeah, sorry.
Like in the Fisher-Rao. Oh right. Okay. No, I asked you. Yeah. Let me put up the slide again.
Yeah, I'm just trying to think about because I think about 2-3 weeks ago we had this talk about LLMs as Markov chains, and
okay.
yeah, I'm just trying to see.
Here I was thinking of where did it go? Yeah, I was not thinking about Markovian properties in time. So what I was thinking of specifically, this is some collaboration we're discussing with Shuigen Liu and Shen Tong about condition. Suppose you have this target distribution, which is essentially like a distribution like over RD. So it has d coordinates, but suppose that so you could think of it as a joint distribution of d variables. And suppose that some of those variables are conditionally independent given others. In other words, suppose I can describe the Markov properties in the sense of conditional independence properties of that distribution according to some sparse graph. Can I use the sparsity of that graph to inform the kernel approximation? That's the question we're trying to think about.
Okay. Yeah. Now I thought that you were trying to infer some Markovian property somewhere. Yeah.
No, but actually, but this ODE is already, I mean, it's already Markov in the sense that it has where did it go? I mean, because it's an ODE of this form.
Yeah. Okay.
So it's very, but yeah, Markovianity in space. I'm hoping. I mean, this is very much work in progress, but I'm hoping this is in some way a way of taming the dimension dependence of these things. So that's the goal.
Okay. All right. Okay. Thank you very much. Any last comments or questions? Okay, seems not. Yeah, thank you very much, Youssef, for the nice talk, and yeah, looking forward to seeing you some other time. And thanks all.
Hope to see you soon. Yeah.
Yeah. Thanks. Bye.
Thanks very much. Thanks again.